Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Jian Kao, who is a Cardis Collins professor at Northwestern, specializing in innovative manufacturing process and systems, particularly in the areas of deformation-based processes and laser additive manufacturing processes. She is the founding director of the University Research Center on Manufacturing Science and Innovation at Northwestern, known as NIMSI. Kao served as an associate vice president for research at Northwestern from 2012 to 2021. She has co-authored over 250 journal articles, 20 patents, and several opinion articles. Kao has been the editor-in-chief of Journal of Materials Processing Technology since 2018. And Professor Kao is an elected member of the National Academy of Engineering, a fellow of American Association for Advancement of Science, and many other organizations. And she is the recipient of many prestigious awards as well, including ASME TED Belitko Applied Mechanics Award and ASME Milton Shaw Manufacturing Research Medal. She served as the president of the SME, North America Manufacturing Research Institute, chair of ASME Manufacturing Engineering Division, and the program director at the National Science Foundation. So today, Professor Kao will talk about physics-based AI-assisted design and control in flexible manufacturing. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Professor Kao by asking one random question as usual. Today's random question is, what is your idea of the perfect day?
The perfect day is today.
Yeah, every day is the perfect day. Yes, that's awesome. Okay, the
Great.
stage is yours.
Thank you very much for the invitation. And so my goal of this talk is to share some high level of the activities of what we do. So in our lab, we have been, looking at both in numerical simulations as well as developing innovative manufacturing processes. So that intersection is really interesting. So the goal is to share, as I said, the high level activities and hopefully to derive some new in detail the discussions later on. So here's the email address, which is the best way to reach me. And with that, let me move forward. So the ultimate goal of our lab is really starting from the materials, looking at the PSPP, process structure property relationships. And the material is the base for, manufacturing processes, right? And then what we added in are those innovative process and machine design. The reason that we want to design our own machine is a capability of, say, imposing a new metrology system so we can have the data that we can analyze, knowing the details about how those data were generated, right? As well as being able to develop new processes. It's hard to do a process development without specific instrumentation. And meanwhile, also to feed back to the process and to do the control. And then the other part is the design. And design, many times you kind of looking at just product, material, and process design separately. The ultimate goal of our lab, as well as my collaborators here in Northwestern, as well as nationwide, is try to also think about co-design of these different aspects. And finally, you know very well, is a qualification and certification that will be needed for this. So overall, linking all these together is the simulation and data. So what we have been doing also last year with my colleague, Professor Wing-Ken Liu, and again, is to look at the how AI and mechanics work together to drive the things that I talked about earlier for process design, for process modeling, and for process control. So what I would do is in this talk, I'm going to talk about these three aspects to show how we do that using additive, metal additive manufacturing as an example. As well as some at the very end, I'm going to show some flexible sheet metal forming process, which is really complementary very well with the metal additive. So with that, uh, so what I want to show you this is our home built laser additive machine. And this is, we call it additive rapid prototyping instrument, ARPI. What it does is a powder blown laser additive process, directed energy deposition. And for this particular one, you can see the environmental chamber, different lasers. And what's up here, actually, I have a more detailed ones later on, is this one. This one, we have RB from the back side. We also have four different hoppers from powder motion labs, as well as two of those, so we can deposit different materials, right? So this is one example that you deposit, for different steels, and you can also mix it. With that, the key questions that we want to ask is, what about the mechanical properties that generated from that deposition? Certainly, porosity is of the concern. And what we did by being close to Argonne National Lab, we put the DD system into Argonne, the high density, high speed X-ray imaging of the DD. So what you can see is the deposit right here, deposit layer here, and the X-ray imaging right there. And we developed a high throughput, uh, sample drum, as well as the deposition, such that we can get lots of data changing the process parameter to see what's happening. And just a glance about, the setup at Argonne. So it's not curved just because of the pictures taken in the panoramic view, right? But the key thing is, if you look at the powder is flowing down, and this is the melt pool. And many people have been doing this for the powder bed. For the DD, we were among the very first group actually doing that. So, but the key thing, there are certain that we did a lot of analysis of this. For this particular group, what I want to say is, the key thing that to notice is also the melt pool dynamics, right? Melt pool is important in terms of how the porosity is generated inside the build. And specifically, we find out for our particular application with the DED is because you are carrying a lot of gas actually into the melt pool. So the melt pool depths, in addition to typically powder bed people looking at the width and the length, so for DED, the depth is actually equally important. So because of that, investigation, therefore, from the numerical point of view, as well as from the practical point of view, we say, okay, how can we control the melt pool depth during the buildup? So the way that we do it is if you look at our experimental setup, you can look at find out the width and the length, right? But the depth is information is not that visible, but numerical simulation can. So we develop our own in-house numerical simulation code called Gamma. And based on this is a um, thermal code basically, and you can see that based on the temperature, you can find out what is the output depth. What's new here is in the simulation, we use the output depth as our target objective function and build up the closed loop control and change the input, which is the laser power, in the simulation. So as a result, the output of this is using one simulation. The output is a laser power history such that you can control the output depth uh, wherever you are, right? So this method is much more general in the sense in terms of the geometry or material property, material types that you are doing. And because of this, what we did, here's a quick glance about the FEM code Gamma. And here's a governing equation, which is pretty standard. And the key part for our particular application is we need the speed in order to do this closed loop control to generate the laser power. So it's being implemented with Python, and CuPy is used for GPU acceleration so that we can do this very good. And you can see that, if you have the constant laser power moving forward, as you build up, the heat got accumulated. Therefore, the output depth is also getting to be higher and higher. But with the constant controlled ones, the laser power certainly is changing as it's decreasing, as you could imagine. And but the output depth is very well controlled. So we implement this to our experiments RP instrument, and you can see also, the heat, the colorization kind of index about, how good is the heat accumulation. And also you can use our camera from the side to also indicate that. What's interesting is also looking at properties, right? So what we did is particularly, let's say, if the goal is whether you can have location-specific control. So we build up a box, and one side of the box has a target output depth as 2 millimeter, and the other side, let's say 1.4 millimeter, different depth. We know that the depth is different, thermal history will be different, so material property will be different, right? So, and that's basically using the simulation tool I mentioned earlier to build up the laser history. And we build the box, and this is A and B. And once from the outside, the geometry, they look pretty similar. But so we cut the tensor specimen from A and B, and then you pull it, So the stress strain curve, the material behavior from A and B are very different, as you can see, right? So this is interesting in the way because many times when you do component design, and sometimes you want different microstructure at different locations to get to the properties you want for, creep resistance, for strength, you have a different design. So this gives you a way to say, using the additive manufacturing, you can actually put the different properties as you need it. One thing also interesting from this one is that particularly if you're a material scientist, you look at this curve, you say, okay, I have a deeper melt pool, which means, I will have a slower cooling rate, and which means potentially I may have, a larger grain size, and therefore, A should be lower than B. So why this A is higher than B? So we specifically actually make sure that we got the specimen at the right location. So one thing interesting came out is that the additive, so what we did here, let's say we just build up the wall and cut mini specimens at these different portions of the wall. And we also use the IR camera to record the time history at different points. And then just purely using the data-driven approach to see, what is the significance of those time thermal history that will influence the properties, the tensor properties right here. So we've done quite a lot of different, checking out different machine learning tool. And this random forest actually comes out to be pretty interesting. So what it does is we put every 50-degree in terms of the time you spend in that 50-degree interval, and then correlate to the strength, say tensile strength of the material. And this plot shows the relevance importance. So what's interesting from purely these data-driven ones, it has two different temperature regions, has the most effect in terms of the property. And the first one, if you look at this, the first one is very much related to the measure the liquidus to solidus temperature. So basically solidification rate. And this is what we were trying to control, right? If we are controlling the melt pool depth, and this is a direct control indication of that. But the second part is equally important in this zoom, is actually very much corresponding to the standard heat treatment temperature. So what this tells us is that the final property that we are getting is a combination of how you solidify it, as well as additional heating time that this material point is experiencing, right? So if you do that, you can come up with just a fitting function right here. And use those walls, we actually fit it, and it's kind of very interesting to see also microstructure wise, it fits this kind of conclusion. One thing is about the spacing, which is spacing. The other one, the heat treatment, is also about these additional delta phase generated that cut the brittle lava phases, and that helped to strengthen the material properties, right? So from here, what we are saying is, okay, we can't just do melt pool control. We actually need to control the thermal history. And thermal history is very challenging things to control, right? Because it's a highly dimensional, temporal, and spatial design. So the way that we do it, we say, okay, if we want to control thermal history, the location-specific control in the previous approach is not going to be enough. So the way that we do it, we use a so-called differentiable simulation. And basically, we rewrite our gamma code using the differentiable simulation, which is basically we use the deep learning library for this particular application. We use the Tai Chi one, but also in another one that we are doing right now, we use the JAX, which is developed by Google. Basically, in those libraries that we got with either Tai Chi or JAX, it has the graph representation about this partial differentiable simulation, right? Partial differential equation. And use a graph, what it can do is it can give you the gradient information for free when you are doing the forward analysis. So it's automatic differentiation provided by those libraries and help us to compute basically this Jacobian that traditionally you have to do it by yourself. So it's a gradient-based continuous optimization, and people have been using differentiable simulation for robotics, path planning, as well as, this is becoming really popular these days to also look at the fluids, heat transfer as we have it right here. So for us, this is what I mentioned earlier, right? We use these tools to develop another tool that for our manufacturing process design. So what it does, it can combine the physics-based simulation, and then what we do is we represent the laser power using a neural network. And here you can think about these are all partial differential equations, in which you can put everything together under a global optimization framework. And with that, what we can say is if I want to have specific thermal history, I can use run this overall simulations and get that what you want. So the key idea is we represent the laser power as a time series and go through the FEM simulation, which is differentiable, get the thermal history, and then we do the optimization. So for example, with this thin wall and multiple points, if the blue is what we want, and we feed into the atom optimization to basically framework, and then create the laser power as this red line, versus if it's constant, it's a green, So as you can see, the green, the thermal response from different points are very different. So we got this laser power history, and then we implement it into RP. So you can see A, B, C, D, depends on where you are. You have different thermal history. And remember, we want that thermal history. So we basically shifted. So this plot is because each point you have a different birth time. So we shifted and compare, for example, the thermal history that we want. The dashed lines are the constant laser power, and these solid lines are the one using our computed laser power. So this is promising. And then the other thing that I mentioned that was interesting is, remember I talked about the second time period, which is important, temperature region is important. So for this one, basically after each simulation, you can calculate the accumulate time and go through the same exercise. And this is, computed from the average point of view. And this is our experiments to also, looking at the time spent there. So the bottom line is it is showing the advantages, but I think there are still more work that can be done to further optimize the optimization tool, as well as the computational the power. So with that, I talk about the process design, and then the next point is about the process modeling. As I mentioned earlier, process modeling needs to be fast enough to feed into this process design. And one thing with the additive manufacturing certainly is a microstructure prediction. So if you look at the powder bed, looking at the microstructure, and typically the best, the best one is people use the phase field method to predict the microstructure. And phase field simulation is pretty expensive. So the question is, typically people are looking at just around the micron size, few micron by few micron, and it could already cost quite a lot. So the question is, how do we speed up this? Because we build a very large part, and the melt pool size is 200 micron, and sometimes could be even bigger, right? So the way that we do this is one example. Looking at the physics embed graph network. So it is inspired by the graph network, but it's not using data training. Okay, so what you can see here is this is the seed grants, and what we do is for each grant, original grant, it treated as a node. So for the node, we have the information such as temperature, grant orientation, and grant volume. And then for the edge is where the physics happening, right? So for the edge is actually we are solving the Allen-Kane equations to look at, you know, how that will actually calculate the liquid solid fractions, also control the grain growth. So that's fixed physics is calculated around the edge. But what it does is it build up the graph network and to do this calculation. So it's kind of reduced order modeling approach. And then you calculate the free energy and then minimize that. So by doing this, you know, this is a comparison between the PEGM model versus the DNS. And as I mentioned, this is kind of the reduced order model, so you have less degree of freedom. And the good thing is, you know, it speed up quite a lot. And because of this, now, first, you know, let's check how it calculate, how it works, right? So you compare, for example, the direct numerical simulation versus the red one is a PGN. And this one you compare, you know, the gram volumes, they're pretty close, as well as the aspect ratio coming out from these two different methods. And this is, you know, reasonably well. And because we can do this, now you can actually model a larger volume, right? Because the computation is very efficient. So now you can calculate a larger volume, and then you can monitor, kind of simulate multi-layers. So what you do is you use the previous calculation as a result, as a seed for the next layer. And with that, we can now simulate, for example, this is 2 millimeter by 2 millimeter, 1 millimeter simulations. And really, you know, interesting, you can see this grain growth, which is actually what also people find out in their simulation. So the idea is if you have these grains, then you can use also crystal plasticity to calculate the mechanical properties, right? And so in the crystal plasticity piece, you know, I don't have time to talk about here, but you can also think about once you have the crystal plasticity, that's still pretty expensive calculated. And then you capture, how do you capture the plasticity behavior also more efficiently? So the way that we do it is, this was back to 2019, and we use the numerical simulation to generate lots of data. So here, you know, because we know the material behavior is also strain pass and low pass dependency, right? So using the design of the element approach, you can generate, for this particular one, we use 10,000 different samples generated. And then using the deep learning network. Basically, for that time, you know, we have the fully connected convolutional neural network as well as the LSTM. And what's new here, the architecture-wise, we also incorporate the initial microstructure into this representation, into this deep neural network, such that it has a good, you know, initial physics. And because of this, you know, you can see the difference between finite element calculated, which are the discrete point about the yield locus, as well as a purely neural network-based calculated as a solid ones. And they match pretty well. And particularly, it could actually also capture the evolution of the network, which numerically, if you do that, it could be very expensive. So overall, you know, right now we are actually trying to develop the whole package. The code is at GitHub, so if you scan it, you can find it. So the idea is, for JAX AM, you can use this one to simulate using the JAX, library, as I mentioned earlier, to simulate the thermal fluids. And with the heat input, you can also, simulate the local grain growth. And with the grain growth, you can simulate the crystal plasticity. And then also we have a FEM version, which you can do the topology optimization. So ultimately, once it's fully built up, you can have location-specific material properties coming from the additive, and do the whole, co-design, as I mentioned earlier. So this is a long-term goal, and we are coming, closer and closer, which I think is very promising. Finally, I want to talk about process control. And so for a process control, one key part is also sensing. And in my lab, we have about 40% numerical computational people, and maybe 60% are experimentalists. Some of the students actually, because they're covering both areas. But the point is, for experimental implementation, we also need good sensing data. So what we do for this one is we use a photodie system, and which was originally provided by Sigma Labs. But what we did is we have these photodie system line up with our laser path. And this is, I believe, the first implementation for the DED system. And use two different wavelengths, calculate the relevant temperature. And then it's interesting that you can see this is the measurement. And if you take the second derivative of this temperature measurement, you can actually corresponding to find the liquidus and solidus temperature. So this is what we find out, the dashed line, the liquid solidus temperature for this Inconel 718. If you look at the literature, there's a large range of the error of values people reported. That's not a surprise, because a little, composition change could change your liquidus and solidus temperature. But the key point is now we can actually in situ measure that. And then when we measure the cooling rate, if you have lower cooling rate, this matches with the existing hardware measurement, which is great. And also for high cooling rate, this one we have a sampling rate could be up to 200 kilohertz. So for this one, we can actually measure high cooling rate that the others were saturated and won't be able to measure. So I talk a lot about the DD, but we also have the high resolution SIM system implement for the powder bed. And the idea is, can we use this as a tool such that we can do in situ closed loop control? So in order to do the closed loop control, first thing that we need to figure it out is make sure the data is not too noisy, because otherwise you are going to get something undesired. If you look at the real-time measurement, this is a different layer assembly about actually this is following the laser path, so the resolution claims could be about 10 micron by 10 micron. So the idea is, if you just put everything together, there's a lot of data, 50 gigabyte data just for this build. So what we did is we used machine learning based to predict the output temperature of the next layer based on the previous layer. So the key message I want to, this is also using the random forest method. The key message I want to come across here is that this definition of the features also involve the physics understanding about what's important. So when we put these things together, it gives us a good prediction. As you can see here, the prediction is almost, you can think about it as a filter. And with that, the noise are gone, but also it still capture some of the fundamental physics right here. For example, this one as a laser turn around, you can see that, first part is lower, and then you can actually, because it's a right turn around, the temperature increase. How much time do I have?
Well, you have a 10 to 15 minutes.
Okay, that's good. Um, So for process control, one thing is really important is actually we have lots of different data coming together. So data fusion or data alignment is important for us. So for this one, we have the machine level control as well as the CT scan, post CT scan, as well as the in situ data. So we put all these together. You can see where the porosity are, and that will help to guide the process design. So it was also interesting recently. We had this sensor array Sigma lab system, as I mentioned earlier, uh, put together with the we went to the Argonne National Lab, and in situ you look from the top of the Sigma lab system, as well as the X-ray, which is a projection, 2D projection about what's happening. So you can see that this is kind of, we treated the X-ray as a ground truth. And you can see this one laser is moving around, and here is the mel pool. And as you go around, you can also see sometimes it leaves, porosity, right? So the key thing, what we are looking for is, we use this as a ground truth, but the question is, can we use the X-rays, the top view, uh, and using this set of the experiments to train um, our model, such that you can just use the sensor array to detect what's happening in the underneath this, right? Which you cannot see that from the top, but you can only see it with the X-ray. So with this goal, these are some details I just skip. So we took lots of data, and so first part is annotation of the mel pool, and then which takes a long time, 1 minute per image, and we have 250,000 images. So this is a perfect occasion to use, deep learning to help us annotate the mel pool. So that's the first step. And then some of the other things, which is not realistic coming from the prediction, we have to remove that based on understanding about the physics after it's done. And then we try to correlate the mel pool depths as well as the top signal, right, coming up. So I should change this. This is already accepted. So the point is, yeah, it's just recently accepted, just a day ago. So the point I want to say this is actually from the top X-ray photodiode system, you can see those peaks. And what's interesting with those peaks is also corresponding to the mel pool depth collapsion. So, many times when we think about this, whether this is a noise or it's really happening, it's actually have some kind of physics involved right there. But the other thing which is interesting is, you see additional peaks right here, which doesn't corresponding to the mel pool depth collapse. And what's happening right here is actually there are some geometric dependency. So the conclusion that we got from this set of the experiment is that it cannot be just the signal. It's actually you need to consider what geometry you are building. So the geometry factor has to take into account whether it's overhand or just solid base. So that's interesting. And the other one, there's a little peak right here, but you don't see anything here. The geometry here is actually very similar to here. What happened is the sampling rate of this one is 200 kilohertz, and this one is just 50 kilohertz. So I think what we did is we pick up something that is kind of missed by the other tool. So lots of data, and actually look forward for the collaborations to analyze those data together. So I want to just kind of finishing up by saying, physics-based and data-driven ones has lots of future for us to look at this qualification, right? So when we look at the upside, the sensing data from the top, we can pick up those things that you won't even see with a detailed X-ray because of the sampling rate. So maybe we can use those data for combined with the simulation. We can do a qualification as we build. So the other part, which I'm going to finish up really quickly, the other process that we do in our lab for the flexible manufacturing process is called double-sided incremental forming. So for this one, we actually build our own machine as well. And instead of using tooling, we use two, as I mentioned, the two tools, geometric independent tools to move around CNC controlled, and you can make very different parts. The challenge for the thing here is because the deformation is all local, so to numerical simulate this, maybe if I take 30 minutes to build it, numerical simulation to simulate really well, it could be easily 2 weeks. So similar challenge in terms of how can we speed it up. And in application of this process is actually, much faster and cheaper to do it, with the various low volume production. So company has already been picking this up. This is Nissan picking it up. And here in the States, there's a Makino Labs also picking up, you can see all these different parts built within a week. And for legacy part, which is particularly challenging, if you have a legacy part, there's no tooling, no drawing available. And using this one, you can actually speed up within a week, but traditionally you can actually take a year or more to get this part. So lots of control also going on. You can do the offline control to do the inline control to get the geometry right. So overall, recently we are also part of the ERC Engineering Research Center, we call HAMMER, which is a hybrid autonomous manufacturing, moving from evolution to revolution. So the idea is you can think about all these flexible manufacturing tools as toolbox, and you can build the part depends on what kind of microstructure, what kind of material properties you need. So the key thing behind this is what I presented earlier, looking at, some of those future directions like mechanistic AI to determine physics needed, and uncertain quantification is important. I haven't talked too much about this, but we have collaborators working on this. Reinforced learning is interesting because then we can also, as well as transfer learning to get to different materials. We can use this for process innovation for simulation tools, as well as sometimes, the human-machine interactions. For example, the incremental forming, sometimes English well, and the other process you have human involved as well. But the other thing I think are very, very critical is also bridges the designers and manufacturers. We need the database. We need the automatic manufacturing process plan generation. We also, I call it functional metrology, basically qualification as you build. So lots of interesting areas to go for. And I would like to acknowledge our group. For sure, without them, we can't do it, as well as our sponsors with the federal as well as the private. So thank you very much.
Thank you. Thank you so much for the wonderful talk. It was very nice. A lot of things are going on here. I can see that. Yeah, it was. Yeah, you're really actively working on wonderful stuff. Okay, let's have a Q&A session. And anyone has a questions, you can unmute yourself and ask questions.
Can I ask a question for your case one? First of all, thanks for the great talk. Yeah, in your case one, you have the neural network connected to a differentiable simulation, and then you calculate the loss, and then update. Do you also update, like both update the neural network and the simulation, or
Yes.
you just okay? How did you update the simulation?
So the simulation is a physics-based simulation, right? So the neural network is really representing the process parameter. So we actually run the physics-based simulation at each iteration. The difference is the physics-based simulation, even in the forward analysis, your gradient calculation is done automatically by JAX or Taiji. So when you do the Adam, on top of that, we have Adam. We use Adam, and basically you use that just to update the process parameter. Does that make sense to you?
I see. And also, like, are there any cases like the model will, like, the interactions between the updates of the weights in the neural network and also like the simulation framework, are there like some trade-off or like some interactions between these two?
Yes. So if you notice, the first time when we tried to do, yes, actually, let me go to the slide. I don't know which one. Let me just, if you, there are too many slides. Oh, sorry. Okay, close enough, I think. Right. So one thing you notice, for example, in case one, the laser power, you see that there's actually have lots of ups and downs, right? The change of the frequency is much more than the case two. For example, this is very, very gentle change. And part of this is because this trade-off, as you mentioned.
I see.
Right.
Okay,
Well,
thank you.
Relate to Jinkai's
Mhm.
question, in order to utilize both the simulation code and the neural net
Mhm.
at the same time, the simulation code must be pretty fast.
Mhm.
But if it needs to be fast, then you have to trade off the fidelity, like the accuracy of the simulation.
Yes. Yes. Yes.
How do you account for that? I guess they
Right.
have a higher tolerance. It's okay to have the high error.
Yeah, so this is, as I mentioned, this is something that even back there, hold on, I think I have a slide to show this. Yeah, this one. This was our kind of, we use a
Yeah, it matched pretty
simulation,
well.
and
Yeah.
and
Yeah.
basically you can see the simulation experiments, right? So it requires calibration for some of those parameters to kind of give us some confidence that we can use it.
Mm.
And certainly we are now modeling, for example, the detailed about the like Lagrangian flow in the simulation, in the experiments. So we are losing some of those physics for sure. And that's why in the current development, I think I have, sorry. try to get to that. Yeah. So for example, in the current simulation, right? So for the differentiable simulation I showed earlier was just for using this part level. But the part level, let's say the temperature input is very much like just a Gaussian temperature to represent the beam, laser beam. But little detail that like what you see, the particle interactions, with Melpool, we didn't capture that. So the goal that we want to develop at this level is to use this as an input to that one, And so the part level could be still computational efficiency for the design, but nevertheless, it's going to be more accurate with more physics involved.
Okay, so more future work is required.
Yeah, definitely.
Okay, Kevin, you want to unmute?
Hi, thank you for the talk. It was very impressive to me. I also have a question about that optimization, about that differentiable simulation combined with the neural network, and what are the example of those trainable variable of the neural network? I guess I can see when you're trying to backpropagate from the physics-based simulation, you get the optimal laser power, right? And
Right.
I guess there is some other like, is this sort of related to how to control that laser power, or?
Yeah, so for this particular one, we just control, we actually, we can control the laser power, depends on, your experimental setup. We can also control, for example, in our experiment, we can also control the base plate temperature. So that's another one you can put in there. I think also, in one of our undergraduate projects, we also developed the cooling nozzle from the side. So if we incorporate that, we can also have the side cooling nozzle locally as another control variable. So I think what variable to control, it's not that much limit in terms of the numerical tool, rather than experimental side, what you can control, how fast you can control.
I see. So I guess this neural network kind of like replacing those physics part, like instead of like implementing all those physics part in the physics-based simulation, I guess is some part is replaced by the neural network. Is that correct? Okay.
Right. Yeah. So the reason we do that, you don't have to do this. I think you can also just using you can also use maybe just some kind of simple function to represent that. The reason that we do that is really just because it's pretty much in the same framework with the differentiable simulation. So you can use that, integration-wise very seamlessly, right? So this is basically your trainable variables, and then you can, it's kind of interpreter from here to here. And you can easily expand that, and depends on what kind of, physical parameters you can control.
I see. Thank you so much. It was a very great talk.
Okay, thank you.
Is there any other question? You can unmute yourself and ask. Well, I was really impressed. I mean, you're able to do the multi-layer and then, analyze the previous temperature layer and then, use that for the next layer. And usually we try to do that as well, but because of the, the computational cost of the high fidelity model we have here is a lot slower than the model you have. It's kind of bottleneck there.
Yeah. So for this particular one, this is measurement. These are the measurement, not the computational. So
yeah, but you train the neural net.
That's right.
To predict.
Yeah, we trained it, becomes really fast. So the the key thing, we actually have a recent paper just accepted on this, is what we learned is that to give you better prediction, you also need to have almost the previous 20, 30 layers data altogether to use to predict the next one. Because for this one, it's easy in the sense that it's only very simple geometry. So the recent paper, we actually look at all these different geometries, and you can see that the neighborhood as well as the previous buildup are very important. So we show that we need the previous 20 layers, or
20.
sometimes even 50 layers in order to give us a good prediction for the next layer.
I see. I see.
And I think the computational time is doable in the way to think about the recoding. The recoding will take time.
Right.
So it's very much doable for that time frame.
I
So
see.
it's not going to be really useful if you want to do following laser point wise. So still layer level control, not laser point and laser path control.
Right. Yeah.
Yeah.
Sounds good.
Uh-huh.
Wow. I think we can learn a lot from you on the 3D printing and the process optimization side. Is there any other question from audience? Well, if not, let's thank our speaker.
Yeah. Feel free to send me email, and love to, have some further conversations.
Yeah. Hopefully we're gonna have more collaboration with you after this
Great.
seminar. Thank you.
Thank you very
So
much.
much for the great talk.
Bye.
Bye.